In part 1, we saw the code that manages drawing and updating our tree of falling leaves. Now, let's look at the code that actually draws the graphics objects, which is all collected in its own tab or file. Most of this file is just taken up by lists like this. This is just a list of x, y values for the outline of the tree. Where did this come from? I drew the tree and the canopy on a piece of graph paper. I made it 800 by 600 because I knew that was going to be my graphics window. And then I plunked down all these little dots that I thought would do a good job of capturing the shape. So I used lots of little lines to make the tree and to make the canopy. I did the same thing for the leaves. I found a nice leaf picture online, so I drew its outline, and I chose little dots all around the outline that I thought would help me capture the shape. I was doing this in Photoshop, so I opened up the info window and I moved my cursor to the center of each one of these red dots. The info window displays the XY coordinates of the cursor, so I just wrote them all down. And you can see I just copied down what Photoshop was giving me. I made the leaf about 1,000 by 1,000, and you'll notice I also marked some of the points with letters. I did this because I knew there would be mistakes, either in this list or as I typed it in. The letters were like little landmarks, and so if something went wrong between C and D, it was easier for me to find which point was the problem. So I typed in 75 XY pairs for the tree. There's about 30 XY pairs for the canopy, and about 55 pairs for the leaf. And again, this is just X, Y, X, Y, X, Y. To draw any of these shapes, I just call draw shape with the array that holds the XY values. You can see it just calls begin shape and wraps it up with end shape. And in between, it runs through the length of the array. In this case, the input array is called verts. So I run up to verts.length, and I call vertex with X and Y. Then I add 2 to my index variable because I'm using XY to draw the vertex, and I just run through them all. That's how I draw the tree and the canopy. The leaf is just a little bit different. Here's draw single leaf. And notice I call push matrix at the beginning and pop matrix at the end. That's because inside draw single leaf, first I scale by 1/1000th. That's because my original leaf ran from 0, 0 to 1,000 to 1,000, and I wanted to go from 0, 0 to 1, 1. So I scale it by 1/1000th. Now that the leaf runs from 0 to 1, I translate by a half vertically, and that puts the center of the leaf where I am now, and then I draw the leaf shape. Here again, we see the beauty of push matrix and pop matrix. When we arrive at draw single leaf, we don't care what's happening in the coordinate system. We know that we're going to do some scaling and translating. So we save the way things are now. We do anything we want to do inside of our routine, and then we go back to our saved point. This means that we're leaving the coordinate system in the very same state that we found it in. Now that we know what's going on inside, let's run the program again. We get falling leaves, and they're completely different every time. Just for fun, I'll show you what this looks like without the tree and without the canopy. Here I've just commented out the calls to draw canopy and draw tree. And you can see the leaves are just appearing somewhere near the top where the canopy would be on top of them, and they fall down, and when they reach the bottom, they start up again at the top. So I'll put the canopy back. So now we can see that the canopy hides the sudden appearance of the leaves. And I'll put the tree back. And now we have the program we started with. Let's quickly look at a couple of other examples of using transformations and the stack. Here I'm drawing a little solar system. The sun is in the middle, the blue box is the Earth, and the Earth has 2 moons in this simulation. We have a little red moon going around the Earth, and we have a smaller white moon, which is a little further away from the Earth, and it's rotating a little bit more slowly. I'm using rotation, translation, and scale to draw these things. To rotate the Earth, I'm just rotating the coordinate system from the center of the sun and then moving out to where the Earth is. I push the stack, and then I move around and change the system, so I draw the moon. Then I pop the stack, push the stack again, and do another set of transformations to draw the small white moon. So the stack lets me save the location of the Earth before I draw each moon. Just for fun, we can replace the squares with something more complicated. The beauty here is this required almost no change. Instead of drawing a circle for the sun, I just called draw duck. And instead of drawing rectangles for the earth and the moons, I just called draw bear. Because everything was being handled with the transformation commands, the rotations and the scaling and the translation, they all work. They don't care what gets drawn after them. And so instead of drawing squares, I'm drawing animals, and it works perfectly. Here's another example. There are 9 of these geometric figures, and they're moving in and out as they all rotate around the center circle. The figure itself is only described once in a little routine that draws it at the origin. Starting from the center of the screen, I push the matrix, rotate, move outward to the center of where I want the object to be, scale it up, and draw it. The program is very short, and because it's based on transforms and using the stack, it's very easy to experiment with this and come up with all kinds of cool variations. You can also have all kinds of happy accidents. This is an example of an early version of the program where I wasn't getting my transformations in the right order. So this is really a bug. This is all wrong. But I really like this, and I think I could build on it to make it even more interesting. So I saved this buggy version just so I could come back to it and play with it one day. I've come back to our tree example because I think it's a very nice illustration of the power of push and pop.